an invitation from Mudao and Maopei, and a nice trip organized by Maopei. Although it is very difficult in the car. Okay, my 2 days talk will mainly talk about the gravitational collapse and the weak cosmic censorship and the formation of trap surface. Okay, my talk will. My talk has 3 parts. The first part will be some basic notations, maybe basic notations and concepts. Okay, most of you may be familiar to these things. Okay, the second part will be the gravitational collapse in spherically symmetric. In spherical symmetric. Spherical symmetry. Okay, this is the work of Crisotolo around in about 10 years, from 84 to 99, maybe. Okay, a series of papers, and the third part will be the formation of trap surface. And black hole, something like that, outside spherical symmetry. Okay, today maybe I will talk concern about the first 2 parts, and tomorrow I will talk about the third part. Okay, so now as we know, the Einstein equation is the Ricci equals A pi T, and when T, the energy momentum tensor is set to identically 0, then it is called a vacuum case. Okay, so okay. First of all, I will introduce some examples of the solution of the Einstein equations. Okay, so the first example will be the Minkowski space. Okay, it is the metric looks like the so it is well known that it is the flat metric, flat, and geodesically complete to any directions. Okay, complete. Okay. So the most important thing about Minkowski space in my talk is the definition of the future now infinity. So this is introduced by Penrose. So so let me draw the Penrose diagram of the Minkowski space. Okay, Penrose diagram. I will use this picture to show you what is the future now infinity. Okay, so the Penrose diagram. So we will say that this means that we can compactify the Minkowski space embedded into a larger space-time. So this means that there exists a larger Lorentz manifold, so that we have embedding. This is the Minkowski space into the larger space-time, such that the pullback of G tilde is equal to conformal factor times the metric of Minkowski. So actually, this is the this definition can be used in any asymptotically fast spacetime. So in particular, I draw the Penrose diagram of Minkowski space here. Okay, so and the omega is required to satisfy omega equals to 0, and its derivative is non-zero on the boundary of Minkowski space in a larger space-time manifold. Okay, so in some textbooks, M2 is called the unphysical space-time. Now, so for Minkowski space, we can in particular find a specified function omega, which can be found in many textbooks, and I will not write it down. So in such a setting, the Minkowski space can be drawn in the picture. Looks like this. Okay. So this is the so I write the Minkowski metric can be written to be dt squared plus dr squared r squared. This is the standard round metric on the sphere. So then this is the r equals 0. And this is the Minkowski space. So in this picture, the Minkowski space is compactified. Okay, so we can identify for example, these slides are the t equals to constant slides, and these slides are the r equals to constant slides. Okay, r equals to constant slides. Okay, so we have a boundary. Okay, a boundary which is 45 degrees. And this boundary is called the future null infinity, square plus, and this is the past null infinity, square minus. Okay, and we still have some points here. This is actually not a point. Okay, this is the spatial infinity, this is the timeline infinity, and this is the past timeline infinity and future timeline infinity. So the most important thing is the future null infinity. Okay, in my talk, the future null infinity will be used in many times. Okay, so we can understand the future null infinity in some other way. For example, the future null infinity can be understood to be the set of n points of maybe future null geodesics. Okay, by this I mean, for example, this is some future null cone from a point. So the end point of this curve is the future null infinity, and in this way we can avoid introducing a conformal compactification. Okay. Okay. And one of the most important features of the Penrose diagram is that the light rays always goes 45 degrees. Okay. This is the most important features in the Penrose diagram, and we can use a feature to analyze the causal structure of a spacetime. Okay, so this is the Minkowski space. Okay, the next thing is the Swatches, which have been talked many times in this activity. Okay, so the second thing I want to talk about is the Swatches. Spacetimes. it is a one-parameter family, parameterized by m, some constant, positive constant. Okay, it looks like g 2m over r dt squared plus. Okay. Minus the r squared dm squared. Okay, so we can see that there are two singularities in this metric, one of which is the r equal to 0, and one of which is the r equal to 2m. So as we know, r equal to 0 is the something like true singularity, or we say this is the curvature singularity. Okay. You can compute curvature approaching the singularity. The curvature will divergence, and it is actually a C0 singularity proved by Jen. Okay, and the R equals to 2m singularity is simply a singularity of coordinate. So we can introduce a coordinate change. So this formula appears many times in our talks. Okay, we define R star to be dr star equals 1 minus 2m dr. Okay, and we introduce the null coordinate t plus r star. Then the Swash coordinate will become g equals to 1 minus 2m over r dv squared plus 2 dv dr plus r squared d omega. Okay, in this coordinate we can see r equals to 2m is no longer a singularity because it is regular on r equals to 2m. Okay, let me draw a picture which is not a Penrose diagram, but just a very naive picture. So this is the r axis, and this is the t axis. Okay, and this is r equals to 0, and here this is r equals to 2m. R equals to 2m. Okay, so in fact, you can see from the this coordinate. So let me investigate the for example, investigate the r equals to constant. We investigate this hypersurface, and we can see, for example, r equals to maybe r naught. Okay, you can see if r not larger than 2m, okay, we can see then partial v. Okay, because this is the let me see. R equals to 2m, and this is the vector field, which is let me see. This is the vector field. Let me see. This is the vector field. Let me see. Maybe. Okay. In fact, in this region, R not larger than 2m, then partial v is time-like. Okay, partial v is time-like. Okay, this is time-like vector field. So the R equals to R naught. This hypersurface is space-like. Okay. So when R not less than 2m, we can see R partial v is space-like. This is because its inner product is positive. Okay, so R equals to R naught is time-like. Oh, sorry. I've, yeah. Yeah. This is a tangent vector field to it. Yeah. Space-like. Sorry? No. R equals to, no. Yeah. This is space-like. Yeah. And when R not equals to 2m, we can see partial V is null. Okay? You can see, yeah, partial V is null. So R equals to R naught is null. Okay? This, of course, this is not a very, very rigorous argument, but you can see outside in the region R larger than 2m, then the null, because R equals to R naught is time-like, so you can find null geodesics which go outside and null geodesics which go inside. So in this region, okay, because R equals to constant is time-like, so but something like this, okay, maybe, okay. This is R equals to R constant. Because this is time-like, so some null geodesics goes outside and some geodesics goes inside. Okay? This is normal. And inside R, in the region R less than 2m, okay, because this is space-like. Okay? This R equals to R0. This is space-like. So null geodesics can only go inside. Okay, can only go inside. So all the null geodesics can only go inside, and null geodesics can only look like this. And all future-directed time-like curves can also only go inside. Okay, actually you can compute that these curves, okay, time-like and null curves, will go to R equals to 0 in finite proper time. Okay, so this is the two region, very different behavior. Okay, so this region is very, very strange, and nothing can escape to infinity. Okay, nothing can escape to R larger than 2m. Okay, so we discovered that nothing can escape from R less than 2m. Okay, this is what we discover. Okay, of course you can also draw the Penrose diagram of Swash Space. Okay, it looks like. Yeah, it looks like this. You know, this coordinate can only cover one of the asymptotically flat region and one black hole region. So I draw the Penrose diagram, just half of the maximal extension of Swash. Okay, and this part. Okay, here this is the R larger than 2m, and this part is the R less than 2m, and this is the R equals 0. Then in Swash space-time, we can also introduce these concepts. So we also have the future non-infinity here. This is the future non-infinity. Okay, the future non-infinity can also be considered as the endpoints, ideal endpoints of the future-directed null geodesics. Okay, so this is the null geodesics, Okay, and the future non-infinity is the set of the endpoints. And here, this is the spatial infinity. This is the time-like infinity. The past time-like infinity and the past null infinity. Okay, and this is the equals to 2m. We have figured out that it is null. So in Penrose diagram, it is 45 degrees. Okay. So you can see anything beginning in this region, okay, cannot go outside because objects can only travel along causal curves, so it can only travel inside this null cone, and it can never escape from this region. Okay, so this is the wave exchange property of the Swash spacetime, very different from the Minkowski. Okay. So let me call this region R less than 2m to be the black hole region of Swash black hole. B, maybe B. And R equals to 2m, actually the boundary of the black hole region. This is the event horizon. This is the event horizon. Yeah, this part is the event horizon. Maybe future event horizon. Okay. H plus. Okay. This is the Swash. And we also have the third notice that the Minkowski space can be included in the Swash family for m equals to 0. Okay. So the third class is the Kerr spacetime. Okay, I'm not going to write down the explicit formula because I will not use the formula in my talks. But notice that the Swash spacetime is maybe you can see it is static. Okay, static means all G. Let me see. Maybe static means that depends the metric depends only on R and the coefficient and the coefficient, maybe coefficient of dT/dr is equal to 0. Okay, this means the static, and it is spherically symmetric. Okay, it means that the Gij, the coefficients only depends on Tr, and static means that it only depends on R. Okay, and it is well known that the Birkhoff theorem tells us that the Swash spacetimes are the only spherically symmetric spacetime. So actually, it is very easy to derive the Swash metric from these two assumptions, but you can. It is in fact the Swash spacetime is the only family of spacetimes which is spherically symmetric. So it means that spherically symmetric plus vacuum. Okay, it's vacuum. It means that T is 0 implies it is Swash. Okay. So the Kerr black hole, Kerr spacetime also contains a black hole. Okay, we can also talk about black hole region in the Kerr spacetime and the event horizons in Kerr. Okay, Kerr is now this is not a static but a stationary. Okay, so stationary. It means that it depends on not depend on. depend on t, but the cross term of t may be dt dr, dt d theta, dt d phi. Okay, the coefficients may be non-zero. Okay, as we know, this is non-zero. Okay, in curved spacetime, and it is not spherical symmetric, but it is SL symmetric. It means that for example, the partial phi is K. Okay, this is curve. So curved spacetime is a generalization of the Swash spacetime. Okay, if the Swash spacetime, Swash black hole is a static black hole, then the curved black hole is the rotation black hole. Okay, it is more complicated, but there is not uniqueness. Okay, so SL symmetric. If a spacetime is SL symmetric, you cannot deduce that it is curved. But if it is a stationary black hole, it is conjectured that this is a curved spacetime. It is a uniqueness of curve. Okay, in analytic case, it is true, but in a smooth case, it is still open. Okay, so this is curved spacetime. Now, let me go to a general asymptotically reflected spacetime. Okay, so for general asymptotically, maybe asymptotically flat, maybe AF spacetimes. Okay, we can define a future now infinity with a well-defined future now infinity. Let me square plus. Okay. Then we can define the black hole region. The black hole denoted by B is equal to the spacetime M G. Okay, M J plus square plus. Okay. I'm not going to explain this notation, but it means that this is a region. This is a region which all causal curves from this region cannot reach the future non-infinity. Okay, so you can see from the Swash, and this is the future non-infinity. Okay, this is future non-infinity represents the R equals to infinity. Okay, this is the infinity. So the black hole region, okay, all things in the black hole region cannot go to the infinity. Okay, it cannot escape this region. Okay. So this is a black hole region. In a general spacetime, we can also define something like define a concept of future now infinity using, for example, the endpoints of the future now geodesics or something like conformally compactification as done by Penrose. Okay, many ways, but I'm just only give a very rough idea. So black hole can be defined to be the region. Okay. The signal from which cannot send to infinity. Okay, why the future now infinity is so important? Physically, the future now infinity is the place. This is the place we do for example, detection. Okay, we do detection. So, for example, the detection of the gravitational wave actually is done at the future now infinity. So we assume at the future now infinity. We are at the future now infinity. Here, for example, we are here, and we receive signals deep in the universe. Something happens here, and the signals then send to infinity, and we receive at the future now infinity. So this is so important physically. Okay. Of course, we are not in infinity. Okay, but this is just an ideal mathematical model. Okay, so once we have a black hole, we can still define a future event horizon. Future event horizon. Event horizon. Maybe H plus to be the boundary of the black hole. Okay, of course if you have the concept of the path now infinity, you can define something like the white hole, and the boundary of the white hole is the path event horizon. Okay, this is the same, but I'm not going to go into the detail. Okay, so this is the definition of a black hole in a general space-time, and I show you what is the behavior of the behavior of a black hole. Okay, we expect in a general space-time the black hole looks like almost the same to the Swatches or almost the same to the curve. Okay, so okay, this is the definition of a black hole. Okay, now we are going to consider the initial value problem of the Einstein equation. Okay, let me consider because I'm going to consider the involved evolution of the Einstein equation to study the gravitational collapse. Okay, so I consider the initial value problem. Initial value problem. Okay, we have at least two kinds of initial value problem. Okay, the first kind is the Cauchy problem. Cauchy problem. Okay, the Cauchy problem. Then the initial data is a the Cauchy data means that it is a Riemannian manifold together with a two-tensor Riemannian manifold with a two-tensor. Okay, this is a three-dimension Riemannian manifold, and this is a two-tensor, and satisfy a constraint equation. I'm not going to write it down because I'm not going to use this equation. Okay, you know this is the constraint. You should have a constraint equation because it is a space-like hypersurface embedded in the space-time. So we have a Gauss-Kodály equation. Okay, so this is essentially the Gauss-Kodály. Essentially Gauss-Kodály, and we want to solve this. We want to solve the Einstein equation. Okay, this is solution, and a result of Schottky-Burckhardt and Garrosh told us that this problem is locally well posed. It means that it has a local solution, local in time, solution local in time, and it is unique up to a diffeomorphism. Okay, so you have a solution. You know you have a solution, and maximal solution. Okay, maximal solution. Okay, so this is a maximal solution, but this film do not tell you any useful information. Okay, because you do not know the information of the future boundary of such maximal solution. Okay, we have a solution, mg, but we have no any useful information. Okay. This is the first kind of the initial value problem. And the second kind is the characteristic. Initial value. Initial value problem. Okay, it has many. Actually, there are also many different kind of characteristic initial value problem. Yeah, but I am going to talk about the initial value problem given on two intersecting null hypersurface. Okay, so this is the null hypersurface. This is null hypersurface. This is null. Okay. Of course, before solving the Einstein equation, you do not know whether it is null. But the initial data is given in a way that it will be null, okay, after you solve the solution. Okay, so yeah, to intersecting null hypersurface. Null hypersurface. So sorry. So these are two null hypersurface. No, hypersurface, and maybe we can call this is a C bar, and this is the C, okay, to null hypersurface, and we can solve the Einstein equation. And in many cases, we can solve the solution in a small neighborhood of the intersection. Okay, we require that actually their intersection is space-like, so the solution will exist. This is the result of Shortcut-Burckhardt. Oh, I forget something like that. And Garage. And this is due to Randall and Luke. No. Okay. Randall's result tells us that you can solve the solution in a small neighborhood of the intersection. Luke's result tells us that you can solve the solution in the whole neighborhood of the null hypersurface. Okay. So this is two types of the well-posed initial value problem, and of course this we have constraint equation in this case, and we also have constraint equation in this case. Constraint. Okay? It also has constraint, but the constraint equations in the characteristic case is much more easier because the constraints are simply some ODEs. Okay? ODEs. Okay, this is elliptic. Okay, this is elliptic. Okay, nonlinear elliptic equation, and this is simply ODEs. It is very easy to solve, and if we use this setting, and well, it is easier to impose some physical, interesting initial data. Okay. This is very difficult, but of course this is also interesting. But if we try to firstly approach some physical problem, maybe we like to choose the characteristic setting. Okay. So okay. Now in any case, we can ask what is the maximal solution looks like, and if it has boundary, and then what is the property of its future boundary? Okay, this is our problem. Okay. as we know, if the data is small, okay, small data, if the data is small data means that the initial data is close to Minkowski, okay, it means that it's close to Minkowski, okay, then we know the solution is global. A global solution means that because we don't have a natural time in the Einstein equation, we have not a background time function, so the global solution means that the solution is future causally geodesically complete. Okay, so anyway, it is a global solution, and also the global solution, which is also asymptotic to Minkowski. Okay? Yeah. This is not necessarily true because some specific solutions are constructed which is global but not asymptotic to some flat solution. Yeah. In spherical symmetry, in spherical symmetry, by Look, Yang, and maybe, yeah.
What kind of solutions?
It is, yeah, some, in fact, so the energy will not concentrate to form a black hole. It will going back. So this is the center, and the energy goes inside and goes outside, and they can construct a solution looks like this. So the solution, so the energy will not radiate to infinity, but it will not concentrate to form a black hole. So yeah.
This is close to Minkowski.
No, not close to Minkowski, but no, not close to Minkowski. Yeah. So yeah, but it is global. Yeah, geodesically complete. Yeah. Okay, but in, for example, vacuum, okay, and in vacuum, and there are many extensions to this result, and I'm not going to talk about that. Okay, so small data, in this case, if data is small, then we have a global solution, which is also asymptotic to Minkowski. So the question is, if we have large data, okay, if it is large data, then maybe singularity will develop. Okay, maybe we have a singularity. Okay, we have a singularities. Okay, maybe we have singularities. Okay. So the question is, if we have singularities, the problem is, this is an argument given by Penrose, that if we have singularities, well, something wrong may happen. Then the singularities, the singularities may be, so the curvature may blow up, approaching the singularity, and it seems that the classical physical law may break down around the singularity, and anyway, but yeah, so Penrose thought that the singularities may cause trouble in physics. Okay, but of course nowadays people do not think the singularity is a trouble. Yeah, actually it is a good thing. Okay, so this is another story. So actually this is a Penrose's conjecture. Okay, so may break the physical law. Classical, maybe. Classical physical law. Okay, This is very, very physical conjecture. Okay. He conjectured that so singularities may cause trouble. Okay. But if we cannot see them forever, then that's also okay. Okay. So he conjectured that, for example, we can never observe the singularities develop arising in the Einstein equations. Okay. Yeah, this is the big cosmic censorship. Conjecture. Maybe some physicists call this the cosmic censorship hypothesis. Okay, they think this is true. Okay, but in mathematical society, we prefer to call this the conjecture. Okay. This is the weak cosmic censorship conjecture. So, okay. So we can never observe or detect singularities in the Einstein equation. So I have said before, the detection is made at the future non-infinity. So, let me say in this way. So, okay. So we make detection at the future non-infinity, and the black hole region, all things in the black hole cannot escape to the future non-infinity. So any signals in the black hole cannot observe by us. Okay, so this is equivalent to say that the singularity are hidden inside a black hole. Okay? Of course, this is not quite a mathematical statement, but yeah. So yeah, the singularities are hidden inside a black hole. Yeah, this is. I think this is the most popular statement of the cosmic censorship. Okay. So we have also another statement about the weak cosmic censorship. Now, so because we detect something at the future non-infinity, and if we, for example, okay, this is the future non-infinity, and something happens here. So we travel along the future non-infinity, okay? If at some time we detect a singularity here, at this time, so the singularity may be here, so he sends signals to the future non-infinity, and we detect the signal from the singularity here. Then, okay, this is the singularity. This is the singularity. And this spacetime is solved from initial data. So if we have singularity here, then we can no longer solve the solution beyond the singularity. So the solution may look like something like this. Okay, this is the maximal solution. Okay, this is the maximal solution, and you can see that the future non-infinity breaks down. Okay, here. Okay, we have a parameter on the future non-infinity. For example, in Swatches, it is the U function. Okay, in Swatches, it is the U function, which is maybe t minus r star. okay, t minus r star, and u varies from in minus infinity to plus infinity in r larger than 2m. Okay? Outside the black hole, the u can vary from positive infinity to minus infinity and positive infinity. Okay? Outside the black hole. Okay? So by this we mean the future non-infinity is complete. Okay? Because this is actually the R5 parameter of the future non-infinity. Okay? The node generators of the future non-infinity. Okay? It varies from in the whole view line. So if we have a singularity here that we can observe, then the future non-infinity stop here. Okay, it cannot be complete. So this is equivalent to say that the future non-infinity is maybe future complete. Okay. Yeah. So, and this statement is actually the if you are familiar with the books of Hawking Alice, this is equivalent to say the space-time is asymptotically predictable. Okay. So in Walk's book, in Walk's textbook, the weak cosmic censorship is stated as the space-time, the solution of the Einstein equations is asymptotically predictable. Okay, so this is almost the same thing, and so this is the weak cosmic censorship. This is the weak cosmic censorship. Okay, so. But this conjecture is, Penrose's conjecture is not true, because we know the examples of naked singularity exist. Okay, so the naked singularity. Okay, naked singularity means that the singularity which can be observed by us. Okay, naked singularity. Okay, so not singularity, not inside a black hole. Okay, so the examples of naked singularity actually exists in which I will talk about later, the spherically symmetric solution of the Einstein equation coupled with a scalar field. Okay, so exists. Okay, so the cosmic censorship, the original, the first version of cosmic censorship is not true, but it is actually natural to conjecture that if these naked singularities are exceptional, okay, so by this I mean that the naked singularities cannot appear in our real world, okay, so now the conjecture can be maybe the above. So now the weak cosmic censorship conjecture. Maybe I write it for short by WCC. Is that the above statement is true, maybe generically. Okay? Or naked singularities are not stable. Okay, this is the cosmic censorship nowadays. Okay, so we conjecture that generically there are not any naked singularities arising in the evolution of the Einstein equation. Okay, this is one of the most important problems in classical general relativity. Okay, so now let me go into the second part, which is the spherically symmetric collapse. And in this case, the cosmic censorship was proved to be true. Okay. Okay, this is basically the work of Christodoulos. Okay. Now we want to simplify the equation. We want to simplify the equation because it is too complicated. We want to solve the equation under some additional symmetries. Okay, so the first thing we will consider is the spherical symmetry. But in vacuum, if we impose spherical symmetry, then nothing survives. It is only the Swash black hole. So we need to add some matter field. So Christodoulos consider the spherically symmetric solution of the Einstein equation coupled with the massless scalar field, whose energy momentum tensor is okay, and Christodoulos consider the characteristic initial value problem. Okay, in spherical symmetry, this is the central line, which is r equals to 0. We call the gamma. Okay, now you consider a characteristic initial value problem from a point. Okay, this is Naucon from a point, and here, this is the initial data. Okay. Okay, the initial data is actually in spherical symmetry because the gravitational part vanishes. Okay, in vacuum it can only be the Swash. Okay, so the gravitational part vanishes, and the only surviving part is the scalar field. So the initial data is simply, for example, the alpha naught, a function which is the partial r. Okay, this we have a parameter by the area radius of the orbit spheres. Okay, r. Okay, this is the initial data, but this is not important in my talk. So you just some function. Okay, initial function. Okay, so we will ask what is the solution. Okay, what is the future? What kind of solution looks like in this case? Okay, now, so we are going to follow Christodoulos' argument to see how he proves the weak cosmic censorship in this case. Okay. Okay. So now we have a initial value problem This is initial data, may extend to infinity, so this may be the infinity. Okay. Now we solve this problem. Now, so if the initial data is small, okay, it can also be proved that it is a global solution, but may not be asymptotic to Minkowski, because actually Christodoulou proved the small data global existence in a very, very, very rough norm. Okay. Yeah, the initial data need not to have decay actually, so you cannot expect that the solution will decay to Minkowski. Okay, but anyway, it exists globally. Okay, so it's small data, it will have a global solution, but if the data is large, it may develop singularities. Okay, maybe singularities here, 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 here. But Christodoulou proved that this is a work in '93. The singularity can only, the first singularity. Okay, I mean the first singularity can only appear on the central line. Okay, this is the first singularity. First singularity can only appear on the central line, gamma.
This is measured by the retarded time, the first singularity.
Retarded, yes. Okay. So, yeah, so we have a first. So we will not have a singularity. So we will have a singularity not on the central line. But actually, Christodoulou proved that the singularity can only appear at the place where r equals to 0. Okay, but r equals to 0 need not to be on the central line. Okay, just like the Swatches, the Swatches singularity, it is not in Swatches space-time. There is no central line. Okay, but if in this case we have a central line here, the singularity can only appear here, the first singularity. Okay, this is the first thing. Okay, the problem is this singularity naked? Okay, a naked singularity. Okay, if this is naked. Okay, if it is naked, if it is naked, so maybe here this is a naked singularity, and this is the initial data. This may be the future non-infinity. So if this is a naked singularity, it means that the space-time will look like this. Okay, this is the future non-infinity and stop here. Okay, and this light cone is regular. Okay, this is regular, but this point is singular. Okay, such example exists. Okay, so this is a naked singularity. Now, if it is not a naked singularity, so it means that if we want to prove that in generically, the picture looks like this. This is a singularity, and it is hidden inside a black hole. So a black hole may be here. So event horizon maybe looks like this. Okay, this is the event horizon. This is event horizon, and we also have an apparent horizon. Okay, apparent horizon. The apparent horizon may looks like something like that. Okay, this apparent horizon A. Okay, apparent horizon, and this is the future non-infinity. And here maybe the spatial infinity, but I do not care about this. Okay, I just care about the future of the initial data. And this is the future timeline infinity. Okay, this may be the aesthetic picture of the singularity which is not naked. Okay, it is hidden inside a black hole. We have event horizon, okay, complete future non-infinity. Okay, this future non-infinity is complete. Okay, we also have a apparent horizon, something like this. Okay, so this is the expected picture. Okay, we want to prove that this is generically true. But theoretically, we can have a plot which is regular. Okay, we can have a plot which is regular like cone. Okay, and then it is connected with the apparent horizon. Okay, this may be true. This may be true, but in this case, the weak cosmic censorship is also true because it is hidden inside a black hole. Okay, but in this case, the strong cosmic censorship is not true. Okay, but I'm not going to talk about this. Okay, but actually, you can see from the picture that if you are someone who can travel inside the black hole and live until you travel, maybe, for example, I travel here to this part. And because the space-time is regular, okay, if I am sufficiently strong, not torn apart by the gravity, so I can live here and I can see the singularity. Okay? Because the singularity sends signals in a small neighborhood. Okay, send a signal here, and I receive signal from the singularity. So the singularity can be seen by local observers, but even though I can receive the signals from the singularity, I cannot carry this information back to you because I am in a black hole. Okay? So in this case, the singularity is not naked. It is not naked because it is hidden inside black hole, but it is not, it is locally naked. Okay? In this case, we call this is locally naked. Locally naked singularity. Okay? This is actually the original thought of the strong cosmic censorship. The weak cosmic censorship means that the singularities are not naked. And the strong cosmic censorship is the singularities are not locally naked. Okay, so the strong and weak, so this terminology came from this consideration, but mathematically these two conjectures have no strong relation.
But now is referring to this Cauchy horizon.
The work of the Fermat and Luke, they consider the Cauchy horizon here. Yeah, but this is another thing different to that kind. They both call it Cauchy horizon, but they almost different things. Yeah. So this this picture can also be accepted if you only consider the weak cosmic censorship. But if you want to prove the whole thing, the strong cosmic censorship is also true, then this picture is not acceptable. Okay. But actually, Christodoulou proved that generically this part do not exist. Okay. So the strong and weak are both true. Okay. This do not exist generically. Okay.
This is still generically within spherical symmetry or outside?
Within spherical symmetry, yeah.
Right. It's really not generic.
Yeah. Okay. Okay, so this is the first step to establish that the first singularity can only appear on the central line. And actually, Crisolo have a quantitative description of the singularity. Okay, so let me draw the light cone from this singularity, and if, for example, if the m over r, m is simply the Hawking mass of the orbit spheres, it is defined by 1 minus 2m over r equals to r in spherical symmetry. Okay. Okay, m is defined by this formula. The m over r, which is a dimensionless quantity, if this quantity tends to 0 along from the past, then this is not a singularity. Okay? So if this is singularity, then this is a singularity, then implies that this quantity do not tend to 0. Okay. So also we have a quantitative description. But we will not use, actually in my talks, basically not, I will not compute anything. Okay, so any formula is, any formulas are not important, actually. Okay, so now the next thing, the next thing is to ask how, in what situation a black hole will form. Okay, so the next thing is the formation of black hole. In what situations a black hole will form? So this is a work of Cristodolo in 91, maybe 91. Okay, so consider the same problem. Of course, if in order to form a black hole, the energy should be sufficiently large. Okay, so the theorem is, now we consider two spherical sections, S1 and S2, with radius R1, R2, and mass M1, M2. Okay, then the theorem is if, so, oh no, there exists two constants which are universal, such that if the mass, okay, or the energy, if the energy between two sections are sufficiently large, okay, this is the this is some quantitative so anyway, it is sufficiently large, but Cristodolo give a very precise quantitative assumption. Okay, so the assumption is larger than C1 R2 delta log delta 1 over delta. Here delta is the radius, the difference of the radius. It is also dimensionless quantity, yeah, because it is divided by R1. Yeah. Okay, so this is called the M. The energy is sufficiently large in this sense. Okay. Oh, sorry. For. Yeah. So, I will talk about this more in tomorrow, because tomorrow I will talk about some more geometric meaning of this condition and other conditions in outside spherical symmetry. Okay, so okay, so in this case,
This condition is actually
this is the assumption. Okay. Yeah. We have a conclusion is
so it doesn't does it imply it's still scalar field, right?
given all the things are within the spherical symmetric solution.
So actually imply conditions are scalar field implicitly through the Einstein equation. Although this M2 and 1 they're gravitational data, but
Yeah, that's true. Yes. So the conclusion is there is a black hole region. There is a black hole region. Actually, the statement is much more complicated, and but I can tell you that it has a black hole. And for example, if S1 here, this point this point can be singular or not singular. Okay, that's all okay. And this is the null cone. Then it is known that the apparent horizon appears before the null cone from S2. Okay, so before S2, the apparent horizon appears. Okay, this is the apparent horizon. Okay. The apparent horizon means the region of 2m over r equals to 1. Okay, so the apparent horizon appears here, but this part we don't know this part. Okay, so we just know some apparent horizon appear before S1, before S2, and goes to infinity, and we have a event horizon. Okay, we have an event horizon. Okay, this is the event horizon. This is the apparent horizon. And moreover, the trap region I mean, actually the black hole region. Oh, sorry, this is not the black hole region. This is the real black hole region, the region inside the apparent horizon. Okay, to m over r less or plus less. Okay, larger than 1. Okay, this is the trap region. Okay, it's terminated at a space-like singular boundary. Okay, it means that this region will stop here, maybe stop here. This is a space-like r equal to 0. This is singularity. Okay? So there will not be Cauchy horizon in this part. Okay, because all the things, the apparent horizon will go to infinity. Okay, all the things are terminate. All the things terminate at the singularity. Okay, so no Cauchy horizon here. This part, but there may be Cauchy horizon here. Okay, we do not know. Okay, so this is the sufficient condition. This is a sufficient condition to form a black hole. So maybe we call this the proof, the proof of step 1. This is the proof, the step 2. Okay, so the last step would be to ask. So the last step is to ask around a singularity. Okay, is this sufficient condition true in generic case? Okay, so the last step. So the last step is the formation of black hole let me mention that no statement about the completeness of the future non-infinity here, but actually the event horizon, in order to define an event horizon, we need to first have a complete future non-infinity first. Okay, so implicitly implies that implicitly implies that the future non-infinity is complete. Okay, this is actually some other related to some previous work of Christopher, but this is the film in the paper in 91. Okay, so the last step is the formation of black hole preceding the singularity. Okay, so now let me consider this case. So let me assume that the singularity is developed here. The first singularity is here. Okay, then this is the Pascal cone of the singularity. So the question is in this formation of black hole theorem, we have a sufficient condition. This is an open condition, okay? But we want to prove generically this thing if there is a singularity. So the thing we want to prove is generically there is a black hole surrounding this singularity. So an open condition is not sufficient. We need to prove that generically this condition is true around if this condition is generically true if we have a singularity. Okay, this is proved by Christodoulou in his 99 paper. Okay, the statement is follows. Okay, let me modify the statement of Christodoulou. Okay, so now suppose that we have a singularity. Let us call it E. Okay, and this is the light cone. Okay, this is gamma, and this is the initial data alpha naught. Okay, then the statement is there exists a function f. Actually, he considered the all initial data lies in the BV space. Okay, BV. So the conclusion is there exists some function f. Okay, such that the solution. So now the solution of alpha naught has a singularity. Okay. Then the conclusion is there exists some function such that the solution of alpha naught plus TF has a black hole region preceding the singularity. Okay, so the solution of alpha naught, okay, in a solution of alpha naught, E may be naked, okay? But if we add a perturbation, okay, for all T, okay? So if we perturb it, so it becomes alpha naught to TF, okay? Then that we will have a black hole, okay? We will have a black hole. Maybe it looks like just the same to this picture, okay? That's the same to this picture. Yeah. This is the space-like singularity, and this is the apparent horizon. This is square plus, and this is the event horizon, H plus this A the apparent horizon. Okay, this is the R equals to 0. This is singularity. Okay, this is a generic picture. So there exists some function f. There exists some function f such that the solution of this has a good property. This is a good picture. Okay.
That's for all T.
For all T, yeah. So let me make some remarks on the proof of not actually on the proof, but
to describe this kind of f in terms of geometry condition.
it is a very special function. We should construct it according to all.
We have equation description of f. Equation of description.
It is actually a very complicated construction. I think no any very easy or obvious equations satisfied by f. Yeah. Yeah. So maybe someone think this is not sufficient to prove the weak cosmic censorship because it's too rough. Yeah. Okay. Let me make some remarks. Finally. By Crystal. Yeah. All the things are Crystal. My result it will appear tomorrow. Okay. So. Oh. Yeah. So the last remark will be oops. The first thing is now as we know, this is the statement of instability of the naked singularity, because in this case, the singularity is not naked. But if we, in a solution of alpha naught, the singularity may be naked, or of course may not be naked. Okay, so this is the instability statement. And moreover, now let me draw the picture. And this is the space of all initial data. Okay, maybe the notation is A. Maybe. Okay, this is the same to that parent horizon. But anyway, the A is the set of all initial data. Okay, and this hypersurface, hyperplane, or hypersurface maybe. Hypersurface is the set of initial data how to say that? Naked. Bad initial data maybe. Okay. Bad initial data. Bad means that the solution of bad things, bad initial data, has a naked singularity. Okay, this is the bad thing. Okay, the other are good. Okay.
Why we only care about the initial data of the scalar field? Why we don't care about other data?
So sorry, I.
The initial surface.
Uh-huh.
Why we only care about the scalar value data field?
Yeah.
Why we only? Why we don't
Not-
care about others?
Nothing survives in spherical symmetry. In spherical symmetry, the only thing is the scalar field. Yeah.
No, I mean, we have an actress multi-formation along IC. IC is just hypersurface. We could not only assign scale value, we could have other small tensorial data.
I don't quite get.
So because the scalar is the easiest example, where the pistol can work out the details.
Oh, you mean?
Others are too complicated.
Okay. Okay. I see. Yeah.
And then that's not the physical problem, it's
Yes.
not the generic problem.
Yes. You are right. Yeah, but other things are very complicated. Yeah, so this is just something like a mathematical practice to understand the whole problem. Yeah, this is a toy model. Yes, yes, very toy model. Yeah, yes, exactly.
Yeah, he's going to talk about that boundary case. Yeah. He's going to talk about a case without spherical boundary case.
Yes, but I will play inside the toy model actually. Yeah. Okay, so let me just give give some. So the statement is if we have alpha naught here, okay, then we can find a family of something like that. Okay. So the whole line are outside the bad initial data set. Okay, and actually Christodoulou have proved an additional statement that if we have another family, this alpha 1 is also a bad initial data, then we can also construct another family. This is alpha 2. This is another family. Okay, then all these families do not intersect. Okay, so this implies that E is of codimension at least one in A. Okay, actually Christodoulou proved that E is of codimension at least 2. Okay, but this is not quite important. Yeah. So this is the first remark, and the second remark is
You could vary alpha I continuous, then we have two parameters. Right? I mean, very.
where is alpha naught?
Yeah, that's another parameter.
No, the parameter should.
I know.
Yeah.
That's one, but you could vary.
Yes, very here. Yeah. Any two families do not intersect. So the next remark is actually the proof is the proof is used to use the above theorem on the formation of black hole. So it is proved that if this is a singularity, okay, and the initial data here, the light cone here, it is proved that for alpha naught plus TF, okay, there resists some point here, okay, some point here, okay, such that the light cone from P will have two sections, okay, satisfying the sufficient condition of the formation of black hole. Let me call this the lower bound condition, because some energy is bounded from below, sufficient large. So this is, we call this the lower bound condition. Okay, so
You have S1 and S2.
yeah. So we will find some point E such that the light cone here will have two sections satisfy the lower bound condition. Okay, LBC, maybe LBC. But I will have many LBCs tomorrow. Okay, LBCs. Okay. So the proof is to find such a P or such a light cone. Okay. Moreover, not just a point, but a sequence. Okay. Actually, it can be found that we have a sequence of P approaching the singularity, maybe P1, P2, Pn, okay, such that all the light cones satisfy the lower bound conditions, maybe in this way, okay, something like that, okay. So here, yeah, two sections, lower bound conditions. So two sections, okay, satisfies the lower bound condition. So this will imply that the apparent horizons issued. So the apparent horizons started from the singularity. There is no Cauchy horizon here. Yeah, this part do not exist because the apparent horizons will approach the singularity. Okay, so this is the final remark. Maybe I think I stop here today. Thank you. Actually, because I mean, so
you have a sequence that approaches.
yeah, because actually I have a sequence of maybe trap surface here, maybe a trap surface, maybe a sequence of trap surface here, approaching the singularity. But the apparent horizon should be before the trap surface. Yeah, so it should be, yeah. Yes. In this case, the apparent horizon will start here. Yeah, so far from the singularity. Yeah, which is not possible in the case.
Do we have any asymptotic behavior of the PI sequence or LBC?
Asymptotic.
We have the data, R1, R2, M1, M2, and that kind of thing. Do we have asymptotic behavior along the sequence?
Asymptotic behavior.
I hope we have
Actually,
a limit so that we can make cryptographical.
Actually, the theorem is quite general. It assumes that this thing is not tensor 0, then it is singularity. Then that point is a singularity. Then it is automatically. It is something like the scale invariant. So.
We don't have a limit.
Yeah, I don't quite understand what you mean. Yeah, so
Because we have a couple of data there, R1, R2, M1, M2, and so on. So as long as there are some condition, of course we could have a variation of the data.
Actually we know very little on the precise behavior. We just know that something like this will satisfy approaching the singularity. Yeah, so
C0, C1, they're not uniform.
this is universal. C0, C1.
For this,
Yes.
this,
Yeah. Uniform. Yeah.